We are continuing our discussion with enthalpy and thermochemical equations. Remember, those are chemical reactions that have a heat involved with them. And we're going to introduce a couple new things. One of them is heat capacity. And you've probably experienced this. If you take a bite out of pizza that fresh came out of the oven, it's that thick stuff too with a lot of tomato paste, you almost always burned your mouth. No matter how much you blew on the thing, man, it burns. The reason why is those very thick tomato pastes have a very high heat capacity in comparison to other foods. That means they store up a lot of heat, and they have to release a lot of heat for the temperature to go down just a little tiny bit. So we're going to talk about those types of materials along with thermochemical equations and do some more predictions with heats and reactions. Heat. What two symbols are used to represent heat? Well, we know one of them. One of them is enthalpy, right? And its units were kilojoules per mole. A second symbol to represent heat is Q. Now that isn't going to be in kilojoules per mole. That's just kilojoules. When heat is produced during a reaction, the system, in other words, the container and the surroundings, it heats up. All right? The temperature goes up. And the calculated heat is negative. That's the convention. You have negative heat. That means that it's energy being lost, energy being given up. When heat is absorbed during a reaction, right? So the heat is being absorbed from the system, from the surroundings. It's going to cool down, right? Things get colder with an endothermic reaction, and the calculated heat is positive. We are going to encounter three types of heat problems. In this first type of problem, this deals with objects that are perhaps absorbing so much heat, what's the new temperature? Or if this object went from one temperature to another, how much heat did it give off? Those are the types of problems that you can handle with these equations. So let's check out these equations and see what the different variables are. Now we know that Q is heat. M is mass. So it could be the mass of an object or just a certain mass of liquid, like 20 grams of water or something. Delta T, we know it's a change in temperature. And the S is specific heat. The specific heat of an object, you look it up in a book. And it's going to be different for different objects and different materials. But usually their units are joules per gram degrees Celsius. And that's what you use to determine the units of everything else in this equation. So that means mass, if you use that type of units for specific heat, mass would have to be in grams. The change in temperature, final minus initial, would be Celsius. And then our heat would be in joules. A second equation to handle these types of problems is Q equals C delta T. So again, Q is our heat. Delta T again is our change in temperature. Final minus initial. And C is our heat capacity. So again, with the different material or different object, it'll have a different heat capacity. And usually they give that to you. And the units are usually something like joules per degree Celsius. And if that's the case, then heat would be in joules, change in temperature would be in degrees Celsius. So which type of problem you're going to use depends on whether they give you the S or the C. Here's the second type of heat problem that we're going to see. Calculations that involve an unknown reaction enthalpy. So you have an incomplete thermochemical equation, and you're going to complete it. You're going to get delta H for that reaction. Here's a typical problem, how it's worded. When 12 grams of iron reacts, 69 kilojoules of heat is produced. What is the change in enthalpy for the below reaction? So now remember, delta H is always in units of kilojoules per mole. So let's divide the number of kilojoules by the number of moles, and we'll get delta H. So the number of kilojoules is 69. And it was given off, so it's negative. Now we calculate the number of moles. We know there's 12 grams of iron. So if we convert that to moles, iron is 55.85 grams in a mole. We'll get moles of iron. 12 divided by 55.85, about 0.215. So my number of moles, 0.215 moles. So a negative 69 divided by 0.215, I get a negative 321 kilojoules per mole. That's my delta H for that reaction. The third type of problem involves calculations with a known reaction enthalpy. In other words, I have a complete thermochemical equation. So let's make this complete. I know for that reaction, I have a negative 321 kilojoules per mole. So I have a complete thermochemical equation. So what type of question could they ask us about that? Here it is. If 29 kilojoules of heat is evolved, how many grams of iron reacted? So remember, the idea with heat is you can treat it like a reactant or a product. And if you have a complete thermochemical equation, you have a mole bridge with heat. So we can straightforward convert 29 kilojoules all the way to grams of iron. All we need is probably some molar masses and a mole bridge. Let's try it. We'll have 29 kilojoules. So I need to convert kilojoules to moles of iron. Then I need to convert moles of iron to grams of iron. In 1 mole of iron, I have negative 321 kilojoules. And the molar mass of iron is 55.85. (29) divided by 321 times 55.85. And I'm just dropping the negative sign because I can't have negative mass. So about 5 grams of iron. So here's a bunch of problems. See if you can get the same answer as me. An iron skillet of 1.28 kilograms is heated to 178 degrees Celsius. The skillet is then cooled to 21 degrees Celsius. How much heat must be removed to affect this cooling? And here's the specific heat of iron, 0.449 joules per gram degree Celsius. Okay, so they gave us specific heat. So you know I had little symbol S. You know we're going to be using this equation then. Q equals ms delta T. So they want us to find Q. That means they had to have told us everything else. Just got to find it. So M is 1.28 kilograms. That may not be the right units though. It's not. Look, G, because S is 0.449 joules per gram degree Celsius. So I need that kilograms and grams. So that's going to be 1280 grams. Just move the decimal place 3 places. Delta T is final minus initial. The final is 21 degrees Celsius. The initial was 178 degrees Celsius. And that's a negative 157 degrees Celsius. So I'm ready to plug and chug. My Q is going to be 1,280 grams times S, 0.449 joules per gram degree Celsius. Change in temperature, negative 157. 1280 times 0.449 times 157 negative 9 times 10 to the 4th. And I want my Q to be negative because that heat is being lost. It's cooling down. Now, before you even read this question, I see an incomplete thermochemical equation. So I already know what type of problem this is going to be. I have to determine the number of kilojoules and divide that by the number of moles to get that. Anyway, let's take a look at the problem. When 23.6 grams of calcium chloride was dissolved in water in a calorimeter, the temperature rose from 25 to 38.7 degrees Celsius. If the heat capacity of the calorimeter and solution is 1258 joules per degree Celsius, what is the enthalpy change for the below reaction? Do you see how to get these two parts? The moles seems pretty straightforward. It's right here. Just use molar mass. You can convert. Let's do that. We'll have 23.6 grams of calcium chloride, and a mole of calcium chloride. Calcium is 40.1 plus 35.45 times 2 for chlorine, 111 grams per mole. So about 0.21 moles. So I have the purple part. I have the number of moles. Now I need to get the kilojoules. And notice they gave us heat capacity. So I'm probably going to use that equation, Q equals C delta T, because they gave us heat capacity. My heat capacity is 1258 joules per degree Celsius. Temperature is final minus initial. Here's final, 38.7. Initial, 25. So my Celsius cancels, end up in joules. So I get about 1.72 times 10 to the fourth. And if I divide that by 1,000, I'll get kilojoules, 17.2 kilojoules. So now I can finally get my delta H. My enthalpy for that reaction is going to be 17.2 kilojoules all over the number of moles, which is 0.21 moles. And if I wanted to leave my answer in joules, I think that would have been fine because they didn't really specify. But 17.2 divided by 0.21, about 81.9 kilojoules per mole. Okay, now is this a positive or negative delta H? Let's check. When calcium chloride was dissolved in water, the temperature went up. So that means it has to be an exothermic reaction. So I had better put a negative sign on that. What is the enthalpy change when 1.2 moles of calcium chloride dissolves in water? So now they're not looking for the enthalpy change for a reaction. They're looking for the enthalpy change when just a certain amount reacts. So another word for this is really just heat. What happens? How much heat is given off or absorbed when this amount reacts? We have 1.2 moles of calcium chloride. And since I have a complete thermochemical equation, I can go from moles of a compound to heat just to pick things out. I have 1 mole of calcium chloride for every, here it is, negative 81.9 kilojoules. So I get about a negative 98.3 kilojoules. 3.51 grams of C6H6. Now that's another name for benzene. It was burned in excess oxygen in a bomb calorimeter. The temperature of the calorimeter rose from 25 to 37.18 degrees Celsius. If the heat capacity of the calorimeter and its contents is 12.05 kilojoules per degree Celsius, what is the value of Q for burning 1.25 moles of benzene? Okay, this is our question that we're trying to solve for. What is the value for Q of burning 1.25 moles of benzene? If you're going to solve that type of problem, you need a complete thermochemical equation. You have to use delta H of the reaction. You need to find that first. So we need to find the enthalpy of the reaction first. Then we can solve the problem. And remember, the enthalpy of these reactions is always kilojoules, some number of kilojoules, all over some number of moles. Now our kilojoules, I bet you they give us heat capacity. That means we're going to use Q equals C delta T. And the moles, they gave us the grams of the benzene. We just need to convert 3.51 grams of benzene. And we'll get the moles. Divide the two, and we'll have our enthalpy of reaction. So let's find our Q first. And that C is 12.05 kilojoules per degree Celsius times the change in temperature, final minus initial. Final is 37.18. Initial was 25. So 12.05 times, parentheses, 37.18 minus 25, close parentheses. I get about 146.8 kilojoules. Now with Q and delta H calculations, always look at the sign before you continue, because very often you have to add that minus sign. We see that the temperature went up, so heat's being given off. This is definitely an exothermic reaction. We know burning is always an exothermic reaction, so that should be a negative sign on that Q. So we've got the Q. Now let's find the number of moles. That number of moles is going to be 3.51 grams of benzene. Just convert it into moles. Carbon is 12.01, so 12.01 times 6 plus 6.06 for hydrogen. I get about 78.12. So that's about 0.045 moles. Okay, so I can use these two to get my delta H. Negative 146.8 all over 0.045 equals a negative 3.27 times 10 to the third kilojoules per mole. So now I'm ready for the last step. Let's convert what they want, 1.25 moles of benzene to heat. 1.25 moles of benzene to heat. So we need the complete thermochemical equation to answer questions like this. That's why we found delta H first. So in a mole of benzene, how many kilojoules do I have? That's the thermochemical equation. We said that we have right here negative 3.27 times 10 to the third. And 1 mole of benzene. So in the end, we get about negative 4.08 times 10 to the third kilojoules. So when 1.25 moles of benzene is burned, we get about 4.08 times 10 to the third kilojoules of heat being given off. What is the enthalpy change to burn 35.8 grams of ammonia? So again, we are going to convert this to kilojoules, to heat. To do that, you need a complete thermochemical equation. Great. They gave it to us. So this should be a pretty straightforward problem. We're going to convert 35.8 grams of ammonia. Just keep converting till we get kilojoules. So we need to get it into moles first, so we can use our mole bridge. And then we're going to use our heat mole bridge ratio. And everything will cancel. We'll have kilojoules. Nitrogen is about 14.01 plus 3 hydrogens, 3.03, about 17.04 a mole of ammonia. We have 4 moles of ammonia for every negative 1267 kilojoules, but a negative 665 kilojoules. So 35.8 grams of ammonia reacts, 665 kilojoules of heat's given off. Here's the last one. How many grams of ethanol are required to provide 358 kilojoules of heat? So now we're just going to go backwards. We're going to convert kilojoules of heat. Go there. But we need a complete thermochemical equation to do this. And they gave it to us. So we're good to go. We can just go ahead and do a straight conversion. 358 kilojoules. We need to convert all the way to grams of ethanol. So first conversion would be our mole bridge, kilojoules to moles of ethanol. Then we can go into grams of ethanol using molar mass. We have a negative 1235 kilojoules for every 1 mole of ethanol. And every 1 mole of ethanol, we have 2 carbons, 2 times 12.01 plus 6 hydrogens, 6.06 plus an oxygen, 16. About 46.08 grams. 13.35 grams of ethanol. I just dropped the negative sign because you can't have negative mass. Okay, so it seems to me this is where everything lies. Everything's surrounded around these 3 types of heat problems. One is where you can calculate heat. Now they also call that an enthalpy change, and they have it given symbol Q. So we have a couple equations for that. Just let specific heat or heat capacity determine your units when you're using that. Then we have 2 types of thermochemical equation problems. One is where they don't give us the enthalpy. They want you to solve it. And remember, the step there is just remember the units for the enthalpy of a reaction. It's the number of kilojoules divided by the number of moles, and you'll get it every time. Then the last type of problem involves those thermochemical equations. They're complete. That means you're given the enthalpy. Just treat it as another conversion factor. And you can convert heat to grams or moles, or you can convert grams or moles to heat using that conversion factor. Good luck.